Hello everyone, this is Professor Kuehn. In my previous lecture, we talked about Benjamin Franklin's 1748 letter to Mr. Peter Collinson. In this lecture, he's describing some of his experiments and observations on electricity. Specifically, what he talked about were his experiments with a Mueschenbroek bottle, sometimes called a Leyden jar. He was trying to determine where in this jar the electrification, or as he would call it, the electrical fire, was being stored. He did a number of experiments, and he concluded, based on his experiments, that the electrification was being stored in the glass itself. He then wondered whether or not this glass needed to be in the form of a bottle, or if he could use a plate of glass to store electricity, and he found that yes, he could. In so doing, he created one of the first, if not the first, parallel plate capacitors. So what I'd like to do is be a little bit anachronistic now, step away from Benjamin Franklin, and talk more generally about parallel plate capacitors and more generally capacitance. So this is a lecture on capacitance and capacitors. Okay. And the reference for this is going to be, it's related to a student's guide, volume 3, chapter 4, on the Mueschenbroek bottle. Mueschenbroek bottle and the experiments of Benjamin Franklin. Okay, so what we should do first of all is describe what we mean by a capacitor. So what is a capacitor? A capacitor is a device used to store electrical charge. To store electrical charge. The Mueschenbroek bottle or Leyden jar is an example of a capacitor. At the end of the previous discussion, what Franklin had done is he had created what is now known as a parallel plate capacitor, which consists of a plate of glass. It doesn't have to be glass, but Franklin's version of it had glass, and then a metal plate on each side. This is a bit like an Oreo cookie. So you've got metal plates sandwiching the glass, and Benjamin Franklin used lead plates. And then what you can do is you can attach a wire to each of these lead plates. This one typically goes to ground. What do we mean by ground? If you take a wire and you wrap it around a metal water pipe, let's say in your house that's sunk deep into the ground, so in other words, it provides an intimate connection to the earth. An intimate connection to the earth. And by intimate, I guess you might say a conductor, like a metal wire that's attached to the earth. And then here, what you can do is you can inject positive charge or negative charge, but more typically, let's say you put positive charge injected onto this plate of the capacitor. So I'll put a little plus sign right here. So what happens when you rub a glass rod so that it's positively charged, attach it to this wire so that the positive charge goes onto here? Well, what happens as the positive charge goes onto this plate, the ground provides a route for negative charge from the earth to be drawn up to here because the negative charge is drawn up toward this positive plate. And also this glass becomes polarized. So let's zoom up on this. So this is a zoomed up view that I'm going to draw now down here of what the glass looks like. So the metal plate on each side has charge. We'll call this, let's say we have positive charge on the metal plate, and maybe I should color these in order to make them more obvious, or I'll color the glass to be blue, and the metal plates, let's make them kind of this shiny reddish color. So the metal plates are red, and the glass is blue. So this is the metal plate, that there is positive charge on it. And again, what Benjamin Franklin means by positive charge is slightly different than what we mean by positive charge. He thought that every object has a level of electrical fire within it, and if it has an excess of this, it's positively charged. If it has a deficit of it, it's negatively charged. We would think about that a bit differently nowadays. We think of positive charge and negative charge as different things, but it doesn't really matter exactly how you think about it. What's important is that you have positive charge on this plate and negative charge on this plate. Maybe I should say something about that, how we interpret positive and negative charge differently today than Franklin did. It's important to realize that most of the scientists who developed the science of electricity and magnetism didn't even know about protons or electrons. The electron wasn't discovered until the late 1800s, I think 1896, by J.J. Thomson. And before then, most scientists thought of positive and negative electricity as being a positive fluid and a negative fluid. So you don't have to commit to the idea of electrons and protons in order to understand the sorts of things that we're talking about here. We'll come back to protons and electrons later, but that's what I guess my point is, that it's not critical to the understanding of what we're doing here. Okay, so we have positive charge up here, so this is positive charge on this plate. And on this plate, drawn up from the earth or from the ground, we would have negative charge. And then what's happening within this glass? Well, the glass becomes polarized. So you have each of the little molecules, if you want to think about it that way. Again, you don't have to think about this in terms of molecules, but the molecules become aligned in a sense. Overall, the glass is neutral, but the molecules are aligned so that the negative ends of the molecules are pulled up for the positive charge, and all these little molecules become aligned or polarized in this way. And you can think about this as the mechanism by which these positive charges polarize this glass, and so there's positive charge down here which draws up negative charge from the ground, like this. So this is the attached to ground, and this is how you charged up this plate positively. I'll just draw a couple more molecules in here, like this, negative, positive, like that. So in other words, the glass is polarized. That is what happens here. And if you get rid of these two plates, as Benjamin Franklin did, and if you have a little bit of this positive charge from here, just sort of a surface charge on top of the glass, and you have some negative surface charge on the bottom stuck to the bottom, you still get this polarization. All that this metal plate does is really make it so that it's easy for the positive charge to slide around on the horizontal surface so that it can provide a shock. Okay, now what you can do after having charged this is, if you want to snip this glass, you could cut this right here, and then you could remove this from whatever the source is, and then you've got this device consisting of these two plates and this glass plate between them, like this. This is your glass plate with the two metal plates on the ends. You've snipped the wires. It's already charged up, so you've got positive charge on this side, negative charge on that side, and now you can carry this around. It stores charge. This positive and negative cannot recombine with each other because it's separated by an insulator right here. You have a device that is able to carry charge around. More modern versions of this use a foil, like aluminum foil, and then a mylar sheet, and then you can kind of roll it up so it looks like, I guess, a ho-ho or something. I don't know if that makes sense to you. I don't know if there are ho-hos still around, but you can kind of roll this whole thing up with the mylar and the two metal plates, like that. And it looks more like a tube with a couple of wires coming out of it like this. So that's another version of a capacitor. All right, so that's a construction of a parallel plate capacitor and a rolled up parallel plate capacitor. Let's go on to the question of how much charge can a capacitor store? How much charge can be stored by a capacitor? Oops. How much charge can a capacitor store? And the answer is, it depends on the size and the shape and the material. Okay, so we talked about a parallel plate capacitor. We can use a Leyden jar. You, in fact, are a capacitor, because if somebody uses a glass rod that's been charged up and touches it to you, you can store positive charge on yourself. You become a capacitor. So every object, every material object is in some sense a capacitor, but some are better at storing charge than others. There's a relationship. There's a relationship between the voltage used to charge the capacitor and the amount of charge stored. There's a mathematical relationship between the voltage used and the amount of charge that is stored. And I'm going to write down this formula, and then I'll be more specific about what I mean by charge and voltage. Okay, so let me move this over to here, as well as this. Okay, and so here I'm going to write down the formula. The charge is equal to the capacitance times the voltage. Okay, so this is the charge stored on the capacitor. This is the voltage of the power supply or the battery used to charge the capacitor. And this is what is called the capacitance. The capacitance is a value, a number that describes the relationship between the voltage you use to charge it and the total amount of charge stored. An object with a larger capacitance will hold a larger amount of charge even when you charge it up using the same voltage. Okay, so a large capacitance implies large charge storage. Okay, so let me explain what I mean by this in a little bit more detail. What do I mean by the capacitance? And I want to use a hydrostatic analogy to try to explain what I mean. So here's a hydrostatic that is having to do with water. Hydrostatic analogy of capacitance. And hopefully this will make more sense to you after I go through this. So let's suppose that we have a well dug in the ground. This is a side view of a well dug in the ground. This is a cylinder. Imagine you have a drill that drills down into the ground and empties out this cylindrical channel into the earth. And then we have another well that is much wider. Okay, so we have two wells. We'll call this well 1, and we'll call this well 2. And this one, if you were to look at the cross-sectional area, that's the area of this hole, we might call that area 1, and we call this one area 2. Now we could fill both of these wells with water to the same height. So here's water filling up both of these wells to some height h. Now here's the question. Which one of these wells holds more water? Well, that should be obvious. It's well number 2 holds more water. Even though they're filled to the same height, because this one has a larger area, the volume of water held in well 2 is greater than the volume of water held in well 1. In fact, the volume of water in well 1 is going to be just given by the area of well 1 times the height, because that's the volume of water is a height times an area. You can see that has units of cubic meters or cubic centimeters. And the volume of well 2 is going to be the area of well 2 times the height of well 2. Okay, so these are volumes, heights, and areas. Don't confuse this V with V for voltage up there. Now, why am I bringing this up? My point is that even though you're using the same height of water, this one holds more volume than this one because the area is larger. Now, here's the analogy, is that you can use the same battery, the same voltage battery, let's say a 9-volt battery, to charge up two different capacitors, and one is going to hold more charge than the other because the capacitance of the one might be bigger than the other. The capacitance in this case is kind of analogous to the area. The charge is analogous to the volume right here, and the voltage is analogous to the height. Okay, so the wider well holds more water, even though the wells have the same height of water. And analogously or similarly, the larger capacitance or the larger capacitor holds more charge, even though it is charged with the same voltage power supply. Okay. Move this out of the way. All right. I hope that makes it a little bit more clear. I don't want you to take this water analogy too far, but it helps in understanding the relationship between these variables. Okay, let me say one other thing before we finish this. Let's talk about the units of this formula. This formula is going to be very useful in the future. And I know I'm bringing up voltage here, even though we haven't really talked about voltage before. You've probably heard the term voltage, a 9-volt battery, a 12-volt battery, and so on. So you have some intuitive sense of what's meant by this. But let me be I'll develop this idea in greater detail as the course goes on. But let me tell you about the units of these for the time being. So charge is denoted by the letter Q, and the units of charge, I'm going to put little square brackets around this, meaning the units of charge, in the MKS system are coulombs. We'll study a little bit about coulomb next week, but the coulomb of charge is named after Augustine Coulomb. By the way, other systems of units for this, in the CGS, this is the MKS system of units, meters, kilograms, seconds. In the CGS, or centimeters, grams, seconds of units, this is sometimes called the electrostatic unit or the stat coulomb, and also sometimes called the Franklin, interestingly. Okay. What else in this formula? We've got charge, we've got capacitance, that is denoted by the letter C, and the units of the capacitance are farads. This is named after Michael Faraday. We'll talk about Faraday later on, but this is measured in farads. And the technically voltage is called electric potential, or just potential for short. The electric potential, which is denoted by the letter V, is measured in volts. So we typically just call electric potential voltage. Technically, it's called electric potential. The units are volts, but just like sometimes we measure distances, we don't say what's the distance the person run the ball. We call it yardage. A yard is a unit of distance. A volt is a unit of electric potential, and yet sometimes people talk about yardage instead of distance. Likewise, people talk about voltage instead of talking about electric potential. Oh, what about the CGS units? For farads, this interestingly is measured in centimeters in the CGS system of units, which you might find a bit perplexing, but I don't have time to go into that right now. And the CGS system of units, volts is stat volts. Okay, so take this as your first introduction to the notion of voltage and charge and capacitance. We'll come back to this stuff more later, but that's a lightning introduction to capacitance and capacitors.